Hello, this is presentation of 캡스톤디자인 project of IT management major in Seoul-Tech. We are Kangmin Kim and Hyunsu Shin. Our service is called Inkover, AI video translation and rendering service. Have you ever watched Korean contents in Netflix? Here, you can see scenes from Good News and The Glory, two shows that gained huge popularity on Netflix. As Korean viewers, we can understand these scenes without subtitles. But let's think from the perspective of international audiences. This is the scene of the last episode of Squid Game Season 1. Let's assume that you are not a native Korean and wondering what's happening in this scene. As you can see, text on the screen is written in Korean. Foreign viewers cannot understand the Korean text shown on the screen at all. They must rely on subtitles, but this creates two major problems. First, subtitles interrupt visual clarity. The black letter box often takes up a significant portion of the screen. In fact, around 40% of global population prefers dubbing contents for this reason. However, even when watching with dubbing, the text appeared on the screen still needs to be translated as subtitles. That means even viewers who prefer dubbing are forced to read subtitles. When dialogue subtitles overlap with on-screen text subtitles, viewers must interpret two different lines of text that flashes by quickly. This creates a major cognitive burden. As media become increasingly global, and especially as Korean content surges in popularity, this outdated localization method has become a barrier to accessibility. This is why we invented a service that automatically translates on-screen text and renders it naturally in the original position inside the video itself. Before building our service, we reviewed prior research. Among them, Strive, published at ICCV, represented the most well-known approach. Let me briefly explain its structure. Strive consists of three main components, excluding pre-processing. First, spatio-temporal transformer network. This deep learning model rectifies the text so that it appears frontal. Next, SRNet. SRNet is a text replacement model that generates a reference frame by inserting user-provided text. The last component is TPM module. This module propagates the replaced text from the reference frame across the remaining frames. However, Strive has several limitations. It requires training three separate deep learning models, and despite using SDTN, it can only handle planar text. Due to mathematical constraint of planar transformations, curved surfaces cannot be processed. Finally, as a research-oriented project, it has very limited user interface support. So we exploited state-of-art zero-shot models, which means that we don't have to rely on complex and time-consuming deep learning processes. We also focused on the ability to handle various situations like card flipping and curved text. Finally, we aim to maintain the original text font and size to keep visuality of the video identical to the original. Therefore, we chose a more intuitive and powerful approach to overcome these limitations. First, we utilize SAM2, allowing users to directly select the target text region. SAM2, developed by Meta, offers highly accurate object tracking. Second, for text replacement, we use Q1 Image Edit, a powerful image editing model capable of preserving the original font style and texture. Third, to extend the result across the entire video, we use the 1.2.2 diffusion model.
Now let me walk you through how these models work together in our pipeline architecture. Our system follows an object-first approach. First, object selection. The user selects the region containing the target text in a reference frame. SAM2 then performs precise segmentation of the selected object. Second, text detection and replacement. Once the object is selected, EasyOCR automatically recognizes the text. After the user inputs the translated text, Q&Image Edit generates a reference image that preserves the original style. Third, object tracking. When the user clicks the tracking button, SAM2 tracks the selected object throughout the video and generates an object mask sequence. Only the object area is masked. The background remains intact. Finally, video expansion. The reference image, masked video, and background frames are fed into the 1.2.2 diffusion model to generate the final video in which the text is naturally replaced across all frames. This is the workflow for translating text. First, we load an object that contains original text. And then, workflow gets a pair of original text and translated text as a variable, and it is inserted in a positive prompt. Finally, an object with translated text is generated using Q&Image Edit model. This is the workflow for masking and creating the final video. This is the section where workflow loads masked video. After that, we combine masked video with the video to create a reference video. And then the workflow loads a reference image generated by Q&Image Edit model. Finally, 1.2.2 uses reference image and reference video to create the final translated video. Next, I'll explain the system architecture. Our design clearly separates the front-end and back-end layers. First, front-end layer. The front-end is implemented using React. The video editor utilizes WebGL to provide high-performance video rendering and real-time previews. Users can intuitively select and edit objects directly on the video. Next, back-end layer. API architecture. We adopted two different API styles depending on usage. First, GraphQL API, used for real-time session management and interactive video operations, particularly SAM2 segmentation, point update, and propagation. GraphQL's flexible structure is ideal for these complex interactions. Next, REST API, used for simpler response tasks such as text detection, image generation, and video rendering. The independence of each endpoint improves scalability and maintainability. SAM2 is used for object tracking, and Comfy UI manages the diffusion workflow, integrating Q&Image Edit and 1.2.2 through modular visual pipelines. Finally, Easy OCR detects multilingual text in video frames automatically. This is the web UI for our service. User can click the object in the video that contains context to translate. The more user clicks the object, the more accurate the segmentation becomes. By clicking the Track Object button, object segmentation is propagated through all frames. And then the Easy OCR module detects text and the user can manually adjust text. After that, the user can enter translated text that will be rendered in the final video. By clicking the thumbnail, the user can initiate Q&Image Edit workflow. Finally, the user can click the Generate Video button to create masked video, which is then automatically sent to the workflow that generates the final video. After workflow is completed, the user can download translated video. Let me show you the final result. This is the same scene of Squid Game we showed previously. As you can see, original Korean text are successfully changed to English text while keeping text style same as original. Finally, let me share our achievements and future directions. We successfully integrated SAM2 into our system, and we implemented context-aware text editing that preserves original font style and texture, making the translated text appear truly native. Finally, from a single reference image, we can generate the HD 24 frames output video with high visual consistency. Our technology can be adopted as a native subtitle system for global streaming platforms like Netflix, Disney, and Apple TV. It enables fully immersive viewing without any additional subtitle layers. Not only for live action content, this technology can be also applied to animation, which has a dramatic rise in global demand. Furthermore, it can significantly reduce localization costs for creator platforms like YouTube and TikTok. However, there are a few limitations to our project. First, The system struggles with complex scenes involving dynamic movement or rapid camera motion. Second, diffusion models still present challenges in consistency and quality. Since we rely on general-purpose pre-trained models, further optimization is needed for specific use cases such as curved surfaces or specific stylized text. Finally, the reference frame generation and video expansion processes currently require significant time and resources. However, we believe these challenges can be addressed through the development and the emergence of next-generation diffusion models. Actually, at this very moment during the presentation, a new model called NanoBanana Pro has been released. As visible on the screen, NanoBanana Pro features substantially improved multilingual text conversion functionality compared to previous model. We hope our technology contributes to a future where language barriers disappear, allowing global audiences to enjoy cultural content more seamlessly than ever. This is end of our project presentation. Thank you for listening.